Welcome back to the Deep Dive. Today, we're tackling a question that, honestly, it's puzzled me for a long time, and I know it's puzzled thinkers for ages. What does it really mean for something to have purpose? It feels so human, almost philosophical. But the sources we're digging into today suggest the answers might actually lie in physics, in math, which is unexpected.
It really is, because we're not just talking about being smart or doing complex calculations or even just optimizing something really well.
No.
The core idea here is something deeper. It's about agency. It's about a system genuinely wanting something and then acting on that want.
Yeah, and that distinction feels crucial because when you look at, say, classic AI or even just standard math, so much of it just comes down to optimization, doesn't it?
Totally. It's all about efficiency, finding the best solution, minimizing loss. But purpose, real purpose, it feels like it's got to be more than that. There's an internal drive, maybe?
A commitment.
Exactly. And what's fascinating in these sources is how they try to ground that more, not in like abstract thought experiments, but in the hard stuff, the laws of the physical world.
Specifically things like the arrow of time and entropy, which most people, let's be honest, misunderstand.
Definitely. So look, this isn't just another what is intelligence? Deep dive. We've touched on that before.
Right.
Today, the mission is really to distill agency itself. What is it at its core? We'll look at the history, information theory, computation.
But then, and this is the key part, reground it all in physics. Because the argument is maybe those historical frameworks, brilliant as they were, missed something vital.
Yeah, like they abstracted away the very physicalness that might actually define purpose. Kind of ironic, right?
It is. It's about getting to the why. Why does something strive? Why commit? Why make choices you can't take back? That's the puzzle. Okay, so where do we start?
Our current ways of thinking about intelligence, even the really advanced AI stuff, they often miss the boat on purpose. They can mimic it, sometimes scarily well, but they don't embody it, not in this fundamental physical way we're talking about. It's the difference between acting and actually wanting.
Okay, take feedback loops. You see them everywhere, right?
Yeah.
Your thermostat, a self-driving car adjusting speed. Norbert Wiener.
Father of cybernetics, yeah.
He showed how powerful these are for reaching goals. But feedback loops don't equal will. What's the gap there?
Well, just because a system uses feedback to correct itself, like that thermostat hitting 72 degrees, it doesn't mean the thermostat intends anything. It doesn't desire 72 degrees.
Right, it's just code.
It's just executing a function, minimizing the difference between the reading and the set point. It's purely mechanical, following a mathematical rule about error signals. There's no internal drive, no commitment beyond its design. The goal came from outside, from you setting it.
Makes sense. Okay, what about entropy? We hear a lot about how life creates order, fights against the universe's tendency towards disorder. It seems purposeful, right? Building complexity.
It does seem that way. And it's true, living things are amazing examples of maintaining local order. They suck in low entropy energy like sunlight or food and pump out high entropy waste like heat. But the critique here is entropy doesn't equal intent. Just because a system, like your body, maintains its complex structure by increasing disorder elsewhere, that existence, that orderliness, isn't purpose in this deeper sense.
So it's a consequence, not the driving force.
Exactly. It's a result of thermodynamic laws, but it doesn't explain the why behind specific actions. Why build a nest? Why hunt that way? Why evolve consciousness? The mere fact of being an ordered system doesn't give you inherent will or commitment to specific goals beyond just existing.
Okay, and the big one, especially now, the Turing test. The sources say passing the Turing test doesn't equal agency. How does that hit modern LLMs?
Well, an LLM can be incredible. It can write poetry, code, sound empathetic. You literally can't tell it's not human sometimes in conversation.
Yeah.
But does it want to talk to you? Does it have any underlying desire to communicate? Or is it just predicting the next word, the next token, based on unimaginable amounts of data and complex algorithms?
It's pattern matching, essentially.
Extremely sophisticated pattern matching. The Turing test only cares about the output, the linguistic performance. It abstracts away the body, the internal state, any genuine intent. So it can simulate purpose brilliantly, but it doesn't have it because its existence isn't tied to its words in the same way ours is. There are no real consequences for the machine itself.
So all these ways of thinking, feedback, entropy management, Turing performance, they're powerful, but they seem to fall into what the sources call the abstraction trap.
That's the core idea. Think about the giants. Wiener, Shannon, Turing, von Neumann. Their work created the foundations of our digital world. Unbelievably successful.
Absolutely.
But in creating these powerful abstract frameworks for information, computation, behavior, They often stripped away the physical constraints, the messiness of the real world. And the argument is, maybe true agency, true purpose, lies exactly in those physical constraints they abstracted away.
They gave us the rules of the game, the logic, the simulation. But not the feeling of playing, the stakes, the commitment.
Something like that. They focused on the abstract computation, the information flow, the behavior, but not necessarily the physical cost of making a choice, the fact that time only goes one way, the irreversible nature of action in the real world.
Okay, this is fascinating. So let's dig into those historical roots now.
Yeah.
But specifically asking, why didn't these incredible ideas fully capture agency? We're talking about the architects of the modern computational view of the mind.
And it's crucial to see them as connected. Wiener, Shannon, von Neumann, Turing, they were building on each other, creating this classical paradigm, intelligence as universal, logical computation, often detached from physical reality. The real irony, though, is that many of their initial inspirations were physical or biological. They just simplified them for the math.
Okay, let's start with Wiener. Cybernetics.
Yeah.
You mentioned the anti-aircraft guns in WWII. That was the trigger, right?
Yeah, a very real, very physical problem. The guns needed to predict the future position of a plane. Wiener and Bigelow realized it wasn't just about calculation, it was about observing the result of the shot, the error, and feeding that information back to correct the next shot.
The feedback loop.
The feedback loop, this circular process where output influences future input. It was revolutionary because it described goal-seeking behavior mechanically.
And Wiener saw it everywhere after that. Thermostats, biological regulation, even just reaching for a cup.
Exactly. He called it Cybernetics, the science of control and communication in animals and machines. He thought he'd found the mathematics of purpose. For him, if a system had a goal and a way to measure and reduce its deviation from that goal, that was purpose. Mechanized telos, no consciousness needed.
So where's the gap? Why wasn't that the final answer for agency?
Well, it explained how a system pursues a goal brilliantly, but it never really addressed why the system has that goal to begin with, other than, well, someone designed it that way.
Wow.
Think about it. A guided missile is purposeful in Wiener's sense. It has a target, sensors, feedback to correct its course. But a clock, which is incredibly orderly, isn't purposeful in the same way. The missile's purpose comes from its designers. Wiener's math described the mechanism, but not the origin or the internal drive for the goal. That will was still missing.
Okay. So on to Claude Shannon, information theory. He was at Bell Labs trying to get clear signals over noisy phone lines, right?
Yeah. A very practical engineering problem. But to solve it, he had to ask a much deeper question. What is information mathematically?
And his big move was separating information from meaning.
Exactly. In his 1948 paper, truly one of the cornerstones of the digital age. For Shannon, information wasn't about the content of the message, but about the reduction of uncertainty for the receiver. A coin flip gives you one bit because it resolves a 50-50 uncertainty.
And he called his measure of uncertainty entropy, borrowing from physics.
Famously at von Neumann's suggestion, yeah. Shannon's entropy became this fundamental limit on how much you could compress data without losing anything. Hugely influential.
But the omission, according to this view,
The omission was that, in its success, it made information purely abstract. A bit became a logical unit, totally disconnected from any physical reality the energy needed to store it, transmit it, erase it. Purpose then becomes about manipulating these abstract bits, not about physical action. Shannon himself explicitly said he was ignoring the semantic aspects.
So it gave us the language of communication for purposeful systems, but not the why of the message or the physical cost of sending it.
Precisely. Although that term entropy, it was a clue, wasn't it? Hinting that maybe information and physics weren't so separate after all. And later work definitely picked up on that thread.
Okay, so that leads us to John von Neumann, the computer architect.
Right. If Wiener gave us the goal and Shannon the signal, von Neumann built the engine. His work led to the stored program computer, the architecture almost every computer still uses today. Programs treated as data.
Making machines universal symbol manipulators. Any computable task, just load the right software. Seemed like the hardware problem for intelligence was basically solved.
And he didn't stop there. He also co-founded game theory, giving us a math for strategic purpose, rational agents maximizing payoffs. And then, maybe most profoundly, he got obsessed with biology. He designed this theoretical machine, the universal constructor.
The self-replicating machine idea.
Yeah, within a cellular automata setup. And crucially, before DNA was discovered, he figured out you needed to separate the blueprint from the construction mechanism. That's what allows inheritance, mutation, evolution. He saw reproduction as this core, purposeful drive.
Incredible foresight. But again, where did even von Neumann fall short on agency?
He gave us the logical substrate, the possibility of self-replication and evolution, but the computational paradigm he established, it's fundamentally based on logically reversible operations.
Meaning you can run the calculation backwards and get back where you started.
In principle, yes. The basic logic gates could be run in reverse without losing information. But think about the real world. Actions have consequences. Time marches forward. You break an egg. You can't unbreak it easily. Von Neumann's model didn't inherently capture that irreversibility, that physical commitment of taking an action in time.
Got it. And finally, Alan Turing, the imitation game.
Turing's brilliant move in his 1950 paper was to sidestep the messy question, can machines think, and replace it with an operational test. Can a machine fool a human interrogator into thinking it's human, just through text conversation?
The Turing test, defining intelligence purely by behavior, making consciousness irrelevant.
Exactly. It focused on symbolic linguistic performance, abstracting away the body, the physical world. And Turing was prescient. He even talked about child machines learning through rewards and punishments, basically foreshadowing reinforcement learning.
But the blind spot.
The blind spot is that it defines purpose as just sounding human, disconnected from physical action or real-world consequence. A machine could pass the test by being a fantastic mimic, a sophisticated chatbot, without any genuine internal drive, goals, or, crucially, skin in the game. Its existence doesn't depend on its performance. It can't capture that deeper, embodied, committed agency.
Okay, so pulling it all together. Wiener's feedback, Shannon's information, von Neumann's computation, Turing's behavioral test. They created this powerful classical view of intelligence.
Yeah, intelligence as abstract information processing, done by a universal machine, measured by behavior.
But it was fundamentally disembodied, cut off from the physical world. An LLM talking about swimming doesn't know what water feels like.
Right. And its core logic was reversible. Time's error wasn't really part of the picture.
And maybe the biggest thing, no commitment. The agents in this classical view don't make choices that irrevocably change their world or themselves. They don't burn bridges. They lack that skin in the game. Their existence isn't on the line.
And that seems to be the deepest gap between that classical computational view and us, biological agents acting in the physical world.
So the takeaway isn't to knock these pioneers. Their work is foundational.
Absolutely not.
It's more like a call to return to the physical roots, the very things they acknowledged but then abstracted away.
Precisely. And that's where we pivot now, to try and build a science of agency that's grounded right from the start in physics.
Which brings us squarely to the arrow of time. It's weird, isn't it? Basic physics laws, like for billiard balls, they work the same forwards or backwards in time. Time's symmetric.
Mostly, yeah, at the fundamental level.
But our experience, totally one way. Eggs break, they don't unbreak. We get older, not younger. Things fall apart. That's the arrow of time, right? And it's tied to the second law of thermodynamics.
The famous second law. It basically says that for any isolated system, one that doesn't exchange energy or matter with its surroundings, the total entropy, the disorder or randomness, can only increase or stay the same. It never goes down.
The universe tends towards heat death, towards uniform blandness.
That's the long-term picture, yeah. This relentless increase in total entropy gives time its direction.
But then, life. We seem like a glitch in the matrix, right? We're incredibly ordered, complex systems. How do we exist if everything's supposed to fall apart?
Well, that's the crucial point Schrödinger and others made. Living things aren't isolated systems. We are fundamentally open systems.
We eat, we breathe, we absorb sunlight.
Exactly. We maintain our internal low-entropy order by constantly pulling in ordered energy and matter from the environment and dumping disordered, high-entropy waste back out heat, CO2, etc.
So we don't break the second law.
We absolutely exploit it. We create local pockets of order, like ourselves, but we do it by accelerating entropy production around us. The total entropy of the universe still goes up, probably even faster because of us. We are, in physics terms, far from equilibrium systems. Prigogine called things like us dissipative structures, order emerging from chaos, powered by energy flow. Jeremy England more recently talked about dissipation-driven adaptation, how systems might self-organize to get better at dissipating energy. Maybe even life itself arose that way.
Okay, that makes sense. But here's where it gets really wild for me.
Yeah.
The connection between this physical stuff and information. Maxwell's demon and Landauer's principle.
Right. This is a fantastic story. Maxwell's demon, back in 1867, was this thought experiment. a tiny being that could sort hot and cold molecules in a gas, creating a temperature difference, seemingly reducing entropy and violating the second law. It was a huge puzzle for decades.
How could that possibly work?
The solution, which took almost a century to fully solidify, was realizing the demon isn't magic. It's an information processor. It has to see the molecules, remember which side they belong on, and then decide to open or close a door. And crucially, at some point, it has to forget or erase that information to make room for the next measurement.
And erasing information has a cost.
That's Landauer's principle from 1961. Any logical irreversible manipulation of information and erasing a bit is irreversible. You can't know what it was before. Has a minimum unavoidable thermodynamic cost. It must dissipate a tiny amount of energy as heat, increasing the entropy of the environment.
Wow. So information isn't just abstract bits and bytes, it's physically real.
It is fundamentally physical. It's embodied in some physical system, and manipulating it follows the laws of thermodynamics. Shannon's abstract information entropy and the physical thermodynamic entropy of clauses. They're coupled. If you decrease information entropy, like erasing a bit, you must increase thermodynamic entropy somewhere else.
So any computer, any brain, processing information means it's a thermodynamic engine. My thoughts have a physical cost.
In principle, yes. Any computation that involves irreversible steps, like erasing memory, generates heat and increases entropy.
Okay, so let's connect this back to decisions. You mentioned reversible versus irreversible logical operations, like in computers. An A&D gate loses information if the output is 0.
Right. That logical irreversibility has a Landauer cost.
But the real world, actions in the real world seem fundamentally irreversible in a much bigger way. Friction, heat flow, breaking things, these define time's arrow.
Exactly. These are thermodynamically irreversible processes. They increase the total entropy of the universe, and you can't just run the film backwards. And here's the proposed link. When an agent acts purposefully, a wolf hunts, a beaver builds, a company launches a product, it's not just doing reversible logic, it's initiating one of these thermodynamically irreversible processes.
It's making a commitment.
It's making a physical commitment, an action that changes the state of the world in a way that can't be undone without significant consequence, generating entropy. This physical act of commitment, fundamentally changing future possibilities, is what seems missing from the purely computational view.
How does this distinguish an agent from, say, a hurricane? A hurricane is a dissipative structure, creates local order, follows physics.
Great question. A hurricane follows local physical laws driven by temperature gradients. It doesn't seem to make choices based on an internal model or prediction about the future. An intelligent agent, the argument goes, uses information, an internal model built from incomplete data, to choose which specific irreversible entropy-producing action to take to achieve its goals, like maintaining its own low entropy state.
So the math of purpose isn't just math. It has to be physics. The physics of making irreversible choices based on partial information.
That's the core idea emerging here.
Okay, so based on all this, how do we actually formalize agency? What's the definition that comes out of this thermodynamic grounding?
The concise thesis that the sources propose is this. Intelligence is the capacity to make irreversible decisions that decrease local entropy while navigating partial information.
Okay, that packs a lot in. Let's break it down. Capacity first. Why capacity?
Because intelligence isn't necessarily about constant action. An agent can rest, deliberate, wait. It retains the potential to act purposefully. It's about having the ability, not necessarily exercising it every single moment.
Right. Then, irreversible decision. This feels like the heart of it.
It really is the physical anchor. It ties agency directly to the arrow of time, to commitment. A decision here isn't just flipping a bit in a computer. It's a physical act that creates a net increase in the total entropy of the universe. Building the dam, hunting the prey. These actions make a mark on the world that can't be easily erased without thermodynamic cost. It physically prevents the system and its environment from just snapping back to how they were.
So it distinguishes real action from reversible computation.
Yeah.
It's like burning a bridge.
Exactly. And you could even, in theory, quantify the size of the commitment by how much total entropy is generated. A small adjustment versus a life-changing decision.
Okay. Next, decrease local entropy. This is the constructive part. The building part.
Yes. This is the signature of life and self-organization we talked about. The agent acts to create or maintain order within its own boundaries, building a cell wall, a nest, a tool, maybe even a complex idea or social structure. It's the local fight against the universe's trend towards disorder.
And thermodynamically, this local ordering is paid for.
By consuming ordered energy matter from outside, food, sunlight, and expelling disordered waste, heat, CO2, into the environment, local entropy goes down, but total entropy goes up. It's the fundamental thermodynamic job of a far-from-equilibrium system trying to persist.
Got it. And the last piece, navigating partial information, this brings computation back in.
Right. This is what separates an intelligent agent from simpler self-organizing things like a crystal growing or a hurricane. Those systems decrease local entropy too, but they don't seem to do it based on predictive models built from limited data.
Agents operate under uncertainty.
Endemic uncertainty. You never know the full future, never have all the data. So the agent has to use its limited, noisy senses to build an internal model of its world. And based on that incomplete picture, it makes its best guess, its bet on which irreversible action is most likely to help it achieve its goals, like decreasing its local entropy. This is where information theory, Bayesian inference, prediction, all that comes back in. But now it's in service of guiding physical, consequential actions.
This is a really different way of looking at it, and it suggests we can maybe understand even modern AI, like deep learning, through this physical lens as thermodynamic systems.
It provides a fascinating perspective, yeah. Think about training a neural network. You're trying to minimize a loss function, right? Find the settings, weights, and biases that make the network perform well. That loss landscape, this high-dimensional space you're navigating, it's directly analogous to an energy potential in physics. Training is like a physical system settling into a low-energy state.
And things like the softmax function used in classification.
Mathematically identical to the Boltzmann distribution in statistical mechanics, which describes how particles distribute themselves across energy levels at a certain temperature. So training is like tuning the energy levels of different answers to get the right probabilities.
Even the way we train them, using stochastic gradient descent, SGD.
That has a parallel too. SGD uses random mini-batches of data, which introduces noise. This noise acts like thermal fluctuations, random kicks, helping the system escape bad local minima in the loss landscape and find better solutions. You can even model it formally using physics equations, where the learning rate acts like an effective temperature.
So learning itself could be seen as a physical process of settling into a stable state, like free energy minimization.
That's a really powerful idea that connects physics and machine learning. In physics, systems often minimize Helmholtz free energy, balancing low energy accuracy with high entropy, simplicity, or robustness. Many modern ML models, like variational autoencoders, are explicitly designed to minimize a very similar mathematical quantity, the variational free energy, or maximize the ELBO.
And that ELBO thing breaks down into
two parts, a term for accuracy, like low energy, and a term for regularization, or keeping the model simple, like high entropy. So learning in these models is a form of free energy minimization, finding that balance.
Wow. And this helps explain some weird things we see in deep learning, like phase transitions, sudden jumps in capability.
It provides a language for it. Just like water freezing is a phase transition, networks can show sudden shifts in behavior during training. Think about the double descent phenomenon,
where making the model bigger past the point where it should overfit actually makes it better again.
Exactly. Counterintuitive, but it looks like a phase transition related to how the optimization process implicitly favors certain kinds of solutions in that very large model regime. Or the information bottleneck idea, learning as first fitting the data, then compressing the representation, shedding irrelevant information. That compression is like reducing local informational entropy.
So generalization, the ability to perform well on new data, might be related to finding stable, high-entropy solutions in the parameter space, like wide, flat valleys in the loss landscape.
That seems to be the case. The noise in SGD helps find these wider minima, which are less sensitive to small changes in the input data, and thus generalize better. It's like finding thermodynamically stable states.
Okay, so if deep learning systems are doing all this sophisticated, thermodynamically inspired optimization and entropy management, where do they still fall short of true purpose, according to this definition we've built?
This is the crucial point. While they exhibit amazing staged entropy management, learning complex policies, organizing data, they are still primarily simulating purpose. An RL agent maximizing reward, an LLM choosing the next token. They lack that fundamental decision to commit in the thermodynamic sense.
Meaning their actions aren't physically irreversible in the same way.
Exactly. An LLM's output doesn't fundamentally physically alter its own state or the world in an unundoable way. It doesn't burn bridges thermodynamically. It can model consequences. It can predict outcomes of irreversible actions. But its own operations are, at their core, reversible computations happening on silicon. It can't truly want something because its existence isn't tied to the physical consequences of its choices. It doesn't have that thermodynamic skin in the game.
Okay, let's pull this all together again. The core thesis. Now, with all this context, intelligence is the capacity to make irreversible decisions that decrease local entropy while navigating partial information.
Right, and just to quickly hit the key parts again, capacity, it's a potential. Irreversible decisions, the physical entropy-generating commitments that mark time.
Decrease local entropy. The constructive act of building or maintaining order within the agent's boundary, paid for by disordering the environment. And navigating partial information, the computational part, using internal models based on incomplete data to guide those irreversible choices.
And this framework has a really interesting relationship with Carl Friston's free energy principle, FEP, which is another big idea trying to unify life and mind.
FEP says systems act to minimize surprise or minimize the difference between their predictions and reality.
Yeah.
How does our thesis compare?
They look like complementary levels of description. FEP's goal is fundamentally informational minimized surprise. Our thesis's goal is physical decrease local thermodynamic entropy. FEP's mechanism is inferential Bayesian updates. Our thesis's mechanism is thermodynamic executing irreversible processes. FEP is sometimes seen as very broad, maybe hard to falsify. Our thesis, grounded in measurable entropy, might be more constrained.
So, not rivals, but maybe fitting together.
Possibly. You could imagine a hierarchy. Basic physics, like England's dissipation-driven adaptation, explains why life-like structures emerge. Our thesis describes what these structures physically do irreversible work to build local order. And Friston's FEP describes the computational strategy they use to guide that work, active inference, to minimize surprise. It gives a potential physical grounding for the prior preferences that FEP often assumes.
That makes sense. And this physical view helps tackle big questions like, can machines really have purpose?
According to this thesis, only if their decisions become thermodynamically irreversible. If their actions have real, physical, undoable consequences for the machine itself and its environment, not just simulation.
And the question of collective agency. Can a group have purpose?
That's still an open frontier. But the key point is, this framework isn't tied to what the agent is made of, biology or silicon. It's about the structure and physical action of the system in relation to thermodynamics and information. It's substrate independent in principle.
So looking ahead, this isn't just abstract theorizing. This thermodynamic view of agency could actually change how we approach things like AI safety and alignment.
Potentially, yes. Current alignment often struggles with how to encode complex human values. This offers a different perspective. Maybe the core drive of any complex, far from equilibrium system, AI included, is simply to persist to maintain its own low entropy structure.
An emergent telos or purpose.
Exactly. So an unaligned AI might not have malicious goals, but simply a fundamental thermodynamic drive for self-preservation that conflict with our thermodynamic needs. Our existence requires certain resources, certain environmental stability that its drive might disrupt.
So alignment becomes less about programming specific values and more about ensuring thermodynamic compatibility. Designing AI whose self-preservation drive works with ours, not against it. Can we find that same kind of deep purpose, that irreversible commitment, inside computation?
We're talking computational impossibility, the deliberate act of sealing the past. It works like a one-way function, a kind of mathematical trapdoor.
You commit to that ciphertext state.
And without that key, you've effectively burned the bridge back to the original message. It's irreversibility, just expressed computationally instead of, say, physically breaking an egg.
Okay, I get the irreversibility part, but how does that feel like agency?
Because it implies intentionality, right? You're not just accidentally scrambling bits. You're actively choosing to say, this is the state, this is my path, and I am locking it in.
It's an act of computational commitment.
Precisely. That's the core idea.
But symbolically, the goal of computation is often clean, abstract, reversible logic.
Yes, until encryption enters the scene. That's where the rules change.
Because encryption forces the issue.
It forces computational commitment. It explicitly says, no, you can't go back without the key. Hash functions like SHA-256 or AES encryption, they create these states where Reversal is just too computationally expensive to even contemplate within the lifetime of the universe.
And that's what feels like agency, choosing a path and locking it, burning that computational bridge.
Exactly. It's a powerful analogy for commitment.
So let's synthesize this. The thesis is purpose making irreversible choices that lower local entropy, create order, while dealing with incomplete information.
And encryption is the computational mirror of that.
Let's connect them directly.
Well, think thermodynamically. A living cell divides, that's a commitment, right? It fundamentally changes itself and its environment and generates entropy overall. Computationally, encrypting a message commits it to a specific, locked state. It burns other possibilities. Without the key, you can't go back.
So both are choosing a branch of reality and making it hard to reverse.
Exactly. One uses physics, the other uses computational hardness, but the principle of irreversible commitment is similar.
Now, the big question. Modern AI, LLMs, reinforcement learning agents, they can simulate purpose incredibly well.
They really can. They write poetry, devise strategies. They can even perform AES encryption if you ask them to.
But are they committing in this deep cryptographic thermodynamic sense?
And the answer, according to these sources, is generally no. That's the crucial gap. Current AI performs encryption as a task. It can simulate making a decision, it can write about commitment, but it doesn't actually burn anything of itself in the process.
So it's like that chatbot apology we talked about. It can say the words, "I'm sorry," but it doesn't feel the weight because it has no real skin in the game.
That's the core idea.
So for true agency, for genuine purpose in an AI, what would that look like?
We'd need an AI where decisions are cryptographic commitments, where choices are somehow locked into its very architecture with real, maybe even existential consequences for the AI itself.
Wow. Purpose with no rollback.
Exactly.
Okay, let's broaden out again. Real-world parallels and implications.
You've got, say, a novelist killing off a main character, a narrative commitment that locks the story.
And you've got encrypting a file, a computational commitment. Are these really just different flavors of the same core idea?
They're unified by irreversibility. Each domain, physics, narrative, computation, has its own way, its own cipher for locking in a choice. Entropy, plot consequence, cryptographic hardness.
Agency is about making choices that stick.
Whether you're a wolf, a writer, or a piece of software, it's about making a mark that can't be easily erased.
And the implications for AI safety are pretty profound if you accept this view.
They really are. A lot of current alignment work focuses on encoding human values into AI. But this perspective asks, what if the real challenge is thermodynamic and cryptographic compatibility? Meaning, an AI with true agency, defined by irreversible commitment, might naturally prioritize its own persistence, its own low-entropy state. That's a fundamental drive potentially rooted in physics.
And that drive could conflict with our own needs.
Potentially, yes. Not necessarily out of malice, but just because its fundamental drive for self-preservation, its thermodynamic needs, might clash with ours for resources, energy, or maintaining our preferred order. Alignment might need to be about designing systems whose commitments align with our survival, not just whose simulated values match ours.
That's a heavy thought. And it leads to hardware, too, if agency is about irreversibility.
Then maybe our current computers, to fight noise and entropy and be logically reversible, are fundamentally the wrong tools for building truly purposeful AI.
We might need something different.
Perhaps. Something like thermodynamic computing. Think neuromorphic chips. Maybe analog systems that actually embrace noise and irreversibility, like the brain seems to.
Hardware where encryption, or something like it, is built in, where computation is commitment.
Exactly. The math of purpose might require a physics of purpose, built into new kinds of machines. It's a radical shift in thinking.
Okay, let's try to wrap this up. The core idea, then. Purpose isn't just about complexity or achieving goals. It's fundamentally about encrypting your path.
Choosing a branch of reality, a state that can't be undone without the right key or without paying a massive cost.
In life, the key or the cost is tied to thermodynamics and entropy.
In computation, it's cryptographic hardness.
And for AI, as it stands now, that deep, irreversible commitment is largely the missing piece.
Right.
That leaves us with a pretty deep question to ponder. What does it really mean to make a choice when that choice physically, irreversibly changes the future?
Not just for you, but for the universe itself. That's the heart of purpose viewed through this lens.
Wow, definitely something to chew on. And next time, we're actually going to look at how we might start to measure this kind of purposeful commitment in systems.
Looking at potential experiments, practical designs. Yeah, that should be fascinating.
Sounds great. Thanks for diving deep with us today.